Yo, welcome back. Today we're working on my custom operating system. Runs on x86, written in Rust. Right now it doesn't do a ton, but we're getting there. It loads from the bootloader loads it. He sets up a memory allocator, sets up logging to the console and to VGA. He has this ability to run unit tests through QEMU. He reads and writes he can read and write the real-time clock. So if I run my little example here, we read the date and then we write the date after and it goes back an hour. He has the ability to parse. He set up PCI. So this should actually have a work with PCI devices. And after he sets up PCI, he can read the Ethernet MAC from our PCI Ethernet card. I think that's the RTL 8139 or something. RTL 8139. And then he can run a little sleep demo where he's logging and sleeping using async await in Rust, which is pretty cool. So that's where we're at. And today's goal is to implement a network card driver. So if we look at main here, right now we have this demo function that we run in the kernel. So we initialize it and just run the demo. And right now all interaction with this RTL 8139, I think it was called. All interaction with that guy is done through just initializing here in this demo. And all we can do right now is read the MAC address. But it would be nice to be able to do some real interaction, get some network packets moving. And so what I thought was a good goal for the day is, sorry, 8139. I thought a good goal for today would be to get reading and writing to the card working through loopback mode. So let's look at the data sheet here. I was skimming the data sheet and I saw this loopback test mode. And in loopback mode is normally used to verify that logic operations up to the Ethernet cable function correctly. In loopback mode for 100 megabit per second, the RTL8139 takes turns the transmit descriptor and transmits them up to the internal twister logic. So I think what that means is if I send a packet over Ethernet and I enable loopback mode, I should immediately get it back over Ethernet. And so that's a kind of good test for me to test the internal logic of my driver. And if we can get to the point where I can just send any data over that and get it back, we're chilling. That's pretty sick. So that's what I want to do today. So the first thing we probably want to do is we probably actually want to start up a Ethernet driver. So we'll call this RTL8139. I think it's called. Check again. 8139. Yep. And maybe this should go into putting in IO. Does that make sense? I was gonna put in IO because it uses IO, the IO subsystem to communicate. Here, let's just quickly run out what IO is. So we have CPU, and he's got some memory, RAM, and he also has these same lines connected to IO. And you basically have to switch between which one of these you're using. So IO is everything that I have that communicates through this subsystem, I have in the IO module. But really, how do I say this? The network card, he's connected like this. But he's also connected like this. There's this thing called memory mapped IO. Calling this RAM is a little bit wrong here. This should actually be memory controller, and he's connected to RAM. And so the benefit of this approach is that you don't need to disable all RAM access in order to access the network card and go through this IO subsystem. You can just access it directly. So putting it in IO doesn't really make that much sense, but that is where my PCI lives. So I don't know. For now, we'll just put it in the middle of nowhere, and I'll figure out project layout later. So we'll just call this RTL8139.rs, and in main, we will import the RTL8139 module. Now, presumably, we're going to have a driver structure that has like internal state, and we'll probably implement some functions for that structure. And one of those will be a new function that returns this guy like this. Which means now we've stubbed that out. In our kernel, we can now say that we have an RTL8139, and he is of type RTL8139. And he gets that structure by importing him from our crate somewhere. The problem is that this guy's not public, so he's not allowed to access him, but now we're good. And now in our kernel initialization, we can create him by saying RTL8139 new like this, and passing him in here. Okay. So we've now like stubbed it out, or we will try to construct the driver, and just for sanity's sake, hello. We'll write out a string from here just to make sure that our code is running the way we think it is. We'll say hello from RTL8139 driver. Cargo run. And we do in fact see that printed here. Hello from RTL8139 driver. So we're chilling. The next thing that we want to do is we probably want a way to get the MAC address out of this thing. Right? And so let's figure out what that looks like. So on initialization, what happens? This guy, let's look up our very handy dandy diagram here. There is also kind of, how do I say this? There's also like our PCI adapter. PCI, which is like those ports, you know, that look like this inside your computer, these guys. And he is also connected to this guy. And the way it works is we talk through IO to the PCI bus. We ask the PCI bus to find our network card. And once we've found him, then we can request through PCI where these lines are located. And so what we need to do is first we need to like take in a reference to PCI, almost certainly, which comes from create PCI mod or IO PCI like this. And from here, now we want to find our PCI device like this. And here we go. We just take this off. PCI, find device. We have some unwraps in here, which is not great. So this guy returns a result option, right? Because he can actually fail to interact with PCI itself, or he might look up this device and not find him. So here we can return an RTL 8139 init error. And we will make this a enum because there are going to be multiple ways that this initialization can fail. One is that PCI probe failed, and we can pass on the invalid header error like this. Or how else can this fail? We can also fail by the device not existing. So we can also say device not found. Those are like our two error conditions here. So then what we do is we try to find the device. And here we go. We'll do this. We'll find the device. And the first way it can fail will map to PCI probe or RTL 8139 init error probe failed, right? That's the first way it can fail. And with this map error will automatically pass in like the previous failure. So we can propagate it up. And then we'll throw a little question mark at it to propagate the error. Then we'll say, okay, or in this case, it's device not found, which even though it's not an error to like run PCI find device and not find it, it is an error here because in order to construct the 8139, we have to find the device. So we'll consider that an error. And now here we can remove this code. So we can say match device. And if it's a general device, we propagate that info, or we say that the PCI header type incorrect. And maybe here we pass in the PCI device type as like a way to flag, well, we didn't get what we wanted, but we got this instead. Why the fuck is that happening? So here we'll say error. Here we need to return an error, PCI header type. So that's the RTL 8139, PCI header type incorrect, and we pass in device. We forgot a closing bracket there. And here we need to write okay now. Let's just comment out this function for a second. Let's make sure that we can like compile. So he's mad because we didn't pass in the PCI bus, and he's mad because we didn't unwrap the result in main. So here in main we have to pass in our PCI, which has to be mutable. Okay, and now we have to say expect failed to initialize RTL 8139. And we need to derive debug for this guy because it's going to print out why it failed, and we need that to be printable in some way. So we just derive debug in a couple places, and I think we're chilling. Cargo check. General PCI device, so we're close. This guy needs to implement debug now. Okay, bing, bang, boom, we are chilling. And let's go back to the, what was this called? RTL 8139. One day I'm going to memorize this number. Okay. So now the question is, do we need to store this device in here? And I think very likely we don't. Because we're only using the PCI system to like ask for the direct access to the object, right? Like here in our previous implementation, let's delete this for a second. This isn't important. What we do is we find the memory base, and then all our like interaction to like find the MAC address is just through accessing memory normally. And so what we should be able to do here is we should be able to copy this. And this is probably what we want. And probably what we can do here is we can find out like the length of this chunk of memory and actually convert this to like a slice that we can just interact with, which is kind of cool. Like, and use our like Rust bounds checking and stuff instead of doing like raw pointer accesses everywhere. So let's kind of look at what that looks like. Where I think it was on PCI. I didn't want to lose this page, so keep that open. And here, under the like generic header type, we have this. But how do we know like how long the address, like how do we know where the end of the range is? Address and the size of the bar. When you want to retrieve the actual base address, make sure you blah, 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 check the lower bits, the 32-bit memory space bars, you calculate bar and this for 64-bit. So like what's weird is nothing here tells me how much of the RAM I'm allowed to use. So how do I know how far up to go? Can we look at this again? So we have base address, card bus pointer, max latency, interrupt pin, interrupt line. So it would be nice, like, how do I know how long it is? I can figure it out by just looking at the data sheet and knowing how many registers are supposed to be mapped. Oh, here we go. To determine the amount of address space needed by a PCI device, you must save the original value of the bar, write a value of all ones to the register, then read it back. The amount of memory that can be turned by... Oh, that's crazy. That's wild. Okay, so let's try that. We'll say let memory size equals 0. We probably have to make this like mutable. Or so here we find the mmap base by doing this. And what we need to do now is maybe we actually want to call this find mmap range. And instead of returning a U32, he's going to return a start and end, or a start and a length. So let's call this mmap range. And start will be a const U32, or a const U8 we should call it. And the end is also going to be a const U8, but I don't like that. I'm going to do length. And, no, that's fine, yeah. We'll convert it into a slice on our end in the driver. I think that's pretty reasonable. Or maybe we'll add like a 2 slice on this guy later. I don't know. We'll see how it turns out. So size can be U size. And now we need to do this mmap range. Let's just delete this code. We're not using it anymore. Comment it out for a reference for later. And now we need to take this loop and let's see. So the first thing to do is to just implement it with nested ifs or a nested thing. So when we find it, we're going to write register. And that doesn't exist yet, so we're gonna go over to here and we're gonna make a write register function here, write register, and config read. We actually don't have a config write function, so we actually have to figure out what this is supposed to be. But we can probably assume that we do the same thing here, where we select a register by writing to this guy. We say like, hey, PCI subsystem, I want to access like 1111. You write 111 there, and then you read from the data port. I think we can probably assume that we can write to the data port as well. But it would be nice to double check that. So configuration space access mechanism 1. Blah, blah, blah. Where do they say? Oh, here. Functions refer to out L and in L Pentium. Nope, that's not what I want. Config address specifies the configuration address is required to be accessed, while accesses to config data will actually generate the configuration access and will transfer the data to or from the config data register. I think that that's pretty much saying that we can just fucking write it. So let's create a like select, split some of this out into a like select register. Is that right? No. Select register is wrong. Okay, what does config read here again? Okay, right. So we read by selecting a bus slot function and then register. So we can here do config write. We pass in the same thing, but we also put in the value, where value is a U32. which means that this guy is indeed going to have a select PCI. Calling it like register feels kind of wrong. We'll say PCI address. I don't know if that's really right, but we'll live with it. So this just takes in all of these guys and does all of this part. Right now, this guy says self select PCI address bus slot function offset, and then reads from him, and config write is just gonna do the same thing. This assertion should actually go in here because it's common. And the write just replaces this read 32 with a write 32. And here we pass in value as a U32, and here we pass in value. Easy. Expected U32. So the problem here is this guy, like this. And we do have some unwraps in here, which is a little crazy. We'll probably come back and fix those later. I don't really want to deal with that right now. I might fix that off screen. So here he says he returns a U32, but we don't have to. And then here we have to write the value. So I think it should just be the bitwise opposite of 0. So all ones, like they said. And we'll say let length is equal to write or read register 4 plus I again. Now we're seeing this 4 plus I pop out in a bunch of places, so we'll say let register offset equals 4 plus I. Right, and we'll say register offset register offset register offset. So I'm seeing something odd here where here the register is multiplied by 4 to get the offset. Okay. Cool. That makes sense. Because the registers are 4-byte aligned. Here, let's just take a quick little peek here. So I was a little concerned because the register accesses. Where the fuck am I looking? Hello? Here, the registers are 32 bits wide. All the register access are 32 bits, but their offsets are still like implemented in byte space. So I was concerned that because I was like doing 4 plus I would get like 5, and 5 isn't a valid offset. But I forgot that in my abstraction, I convert a register to an offset here, so we're fine. We are fine. Okay, so and address should be this. And let's print line end address, or I guess we can just return here. Base address, good, and end address will probably be the same thing. So we'll say, say let start is this. Is that what we called the range here? Start and length. Yep. So start is this as a const u8. And end, oopsies, we're going to do the same thing. End is the base address. This should now say end address. And let length is end offset from start. Okay. And now we can return our mmap range start length. Easy. Length, we'll call it an I size for now, and we'll make this debuggable. And let's just kind of see what we get from this. So in our RTL driver, we have find mmap base, and we'll call this range. And now we'll just print it and see what we get. Non-primitive cast cargo check. Let's see what he's bitching about. Right, because we're doing this stupid conversion here. Self is not valid anymore, and we don't need to mute this because it's already a mutable reference. mmap range is a private type, so we just need to fix that up real quick, which can be done here, pub, and we'll just make these public for now. Cool. Cool. So let's cargo run it and see what we get. We do get a start and a length that is positive, and is that length like fucking bonkers badonkers? It does seem really long. Like, insanely long. What is that in bytes? Okay, let's go back here. RTL, we'll go back to the RTL, and we'll print it with, we'll just print the length now. And we'll print it as, hex, maybe. mmap range length. So what is that? That's 2 to the... That's a lot. Let's see. Let's divide this by 1024. How many kilobytes is this? 2,000. This is like 2 megs? Is that crazy? 20 megs. That's wild. Why is it so high? That doesn't sound right at all. Let's go back to the bar section here where it tells me how to find the memory size. So the type field, blah blah blah. When a base register is marked as prefetchable, means you don't have to read side effects. Blah 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 blah. Hardware is also used to sure. Address and the size of the bar. When you want to retrieve actual base address, make sure to mask lower bits, right? That's what I did before. For 64-bit memory space bars, which I'm not in, for IO space bars, oh, maybe I am in 64-bit, even though I'm in 32-bit memory space, because PCI maybe doesn't know that. Maybe? Plus bar x plus 1. Oh, but I don't have that, so that's fine. For IO space bars, you have like bar and blah, blah, blah. Before attempting to read information about the bar, make sure to disable both IO and memory decode in the command byte. You can bar info. This is needed in some devices as are known to decode the write of all ones register as an unintended access. Okay. That's fine. You must save the original value of the bar, write all ones to the register, then read it back. The amount of memory can be then determined by masking the information bits and performing a bitwise NOT. Performing a bitwise NOT and incrementing the value by 1. The original value of the bar should still be restored. Should then be restored. What? The amount of memory can then be determined by masking the information bits. Done. Performing a bitwise NOT and incrementing the value by 1? What the fuck? Okay, let's try that. The amount of memory. Jesus. Okay, so, we mask bitwise NOT and then plus 1. Okay, this should be U size. Fuck it. Sure. Let length equals length as U size. I size. Now it's 0 because I divided a bunch of times. So let's go back to the RTL driver. That is like a sane size. What in the actual fuck? I wonder why they do it like that. And then I need to write back the original value. So here we do the same thing, but we return the base address. Very, very odd. But we do know that 256 looks sane, because let's go back here and look at like the register list. This does go up to 00FF, which they say are reserved, but that's sane. That's crazy. I would never have expected that that's how you do it. I wonder where I learned that info, but oh, here, they have a reference. Okay. This does not seem like it's... After reading the dev and van ID and the BIOS read series FFD base address and read the value back, all lines on your card will decode. This card has to deliver ones for all internal address lines. Blah blah. This trick to BIOS can determine your required memory size. Where does this come from? This is such a weird reference. Where is this from? This is some guy talking to Yahoo Zinx. Very strange. But I guess we'll just assume it's true. It is true, but we've like got some positive info there, but it's just weird. I don't like it. But that's okay. That is okay. Okay. So in the RTL, we come back here and we know that the mmap range should be 256 because that's what we see in the datasheet. And if it's not 256, that means that our driver is like working with something unexpected. So we can actually, maybe not asserting's a little strong. We can, because really this is IO and it's not like a code error if we get something back from the device that we don't expect. That's more of like a driver unhandled behavior. So we can say mmap range unexpected, and we'll inject the size here as some debugging info. And we'll say if mmap range length is not equal to 256, return mmap range unexpected. So this is actually an error, and this is an error of type RTL8139 init error. And here we go, and then we'll return mmap range length as part of it. Okay, and here we can turn length from an I size to a U size now that it's actually an always positive number. Okay. This is so weird. Is this something like 2's complement or something? Invert and +1. Oh, you know what? Maybe that's actually sane. Because if you want to be able to support the whole memory range. Nope. Not seeing it. Not seeing it. I'm sure there's a reason that this makes sense, but I'm not gonna dwell on it. Okay. So now we can convert this to a slice. So we can say let data or mapped memory equals core slice from raw parts, and we get the mmap range dot start and the mmap range dot length. And I think we want like from raw parts mute actually, because we want to be able to write these guys. Okay. We're close. This guy has to be a mutable U8 for this to work. And now he's complaining this is unsafe. So we just womp womp, throw this guy at him. And now we return the mapped memory as part of the driver. Bing, bang, boom. And this is just a you mute U8. But he's static. Cargo check. We're close. He doesn't like that because in PCI we're making him from a const instead of a mutable. So we'll just throw a little mutable on this guy. And we're chilling. Okay. So now in our RTL, let's go back to this Mac thing. And we'll just call this print Mac for now because I don't want to figure out like a Mac address type and we don't really need it anywhere. And all this guy does is he prints log Mac, we'll call him. And Mac address, we don't have to say we were retrieving through memory space anymore. That's not interesting to us. And the Mac is just self memory, mapped memory, 0 to 6. And we probably need to go like this. Okay. So now we have our driver, and in our demo, we can just say, on this guy, let's log the MAC address. And let's see what happens. Cargo run. And we do, in fact, get 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, which is the MAC address we're passing in for testing. So we're chilling. So here, let's just say stub out driver. And this was finished at around 36 minutes and 50 seconds into stream. And we'll call this done. We will commit this now because it's a useful checkpoint. And we'll say git add everything. And we'll say this is a stub out RTL 81. Oh, I forgot again. No, 8139 driver. Currently, the driver does not do much of anything. However, it does correctly log its own MAC address in the demo. Okay. We should also lint here. So we need to run cargo format and cargo clippy. And we go to main. Oops. There's some unused imports here, this guy. And in main, we also don't use PCI device or get bits. Like this. And these braces aren't needed anymore. And we'll lint again. Cargo format. Lint again. Okay, everything passes. So quickly add -u and git add source RTL, the core of this. And we'll also say replace previously instantiation of PCI stuff. PCI we'll just say we'll say supporting changes. Move the RTL 8139 demo stuff into the. That's not really a supporting change. But we do want to say that we move the demo code for the RTL 8139 into its own driver. Currently, the driver does not do much of anything. However, it does currently log its own MAC address in demo. I'm happy with that. Okay. And we just lint again just to double check that I didn't miss anything. Okay, cool. Let's go again. So now that we have the MAC address, let's like actually start like working with the card. We have our way of working with it, and we can start moving and grooving. So first we need to send 0x00 to the config1 register to set the LWake LWT pin to active high, which should essentially power on the device. Oh, wait. First, I need to enable PCI bus mastering. What does that mean? This allows the NIC to perform DMA. To do it, you can read the command register from the device PCI's configuration space. Set bit to, then write the modified command register. Note that this has nothing to do with the command register that we evoked in the following sections. Okay, well, sure, I guess we'll do what it says. So this is the command register. Mastering. So set bit 2, bus mastering bit. Bus mastering. So I don't see any of these saying bit 2. This is 0x80, which is like bit 7, 8. Command register. Which one of these? Okay, so how do we find like command register? So in the general section, well, let's get the common first. Command. Here we go. Bus master. Okay, sure. And where bus master says set to 1 if the device can behave as a bus master. Otherwise, the device cannot generate PCI accesses. Okay, I'm happy with that. So here we need to enable bus mastering. And this is something that can be done on any PCI device. So here, let's go back to our general PCI device. Really, this should be something common to the general and the bridges, but we don't have bridge implementations right now. But I guess we do have like our underlying implementation, which is called this PCI address thing. So we'll just enable bus mastering here. And so he needs to read the command bit, which is register 1. So we read the register. Read offset 4 equals register 1, where the command register is. So we'll say let status command is this. Status command, then set bit 2. Right. Easy. We actually need to pass in PCI here, because we don't have access to like the registers that we need. We set bit 2 to true to enable bus mastering. Bus mastering bit is bit 2. And then we write this back. Config write status command. And we're almost done. Let's just set the status command offset equals 4. Because we're using this in multiple places. Which is what's my offset here? U8, U16, config write is, offset is U8, yep. So let's just put this guy in here. Status command offset. Okay. Very cool. And this doesn't need to be public because literally no one outside this class can even read these. And now we'll just say, we'll pass this guy through. So we'll call this enable bus mastering on the generic device. Like this. And he calls the inner one PCI, like this. Easy peasy, lemon squeezy. Remove the extra argument. What doesn't he like? Okay. Cool. Now from the RTL 8139, I can say RTL device enable bus mastering. And we need to make this guy public. And we need to pass in PCI here. I guess we do this after we map the memory. Require, and we'll say this is required for the card to write to memory. I think that's pretty reasonable. Okay. Okay. So now we can turn it on. So I think everything else in here is in the space of this memory space. So let's just start looking at this. Config 1 register is offset 52. So where is that in here? Config 1 here, offset 52. Okay. So now here, let's start just defining register offsets here. So we'll say const config 1 offset is a U size with length with this 0x52. And now we can say mapped memory config 1 offset. What does he say to do? He says to write 0x0. And this turns on the card. So let's actually split this out into like a named function so that its use is like obvious. So we'll say turn on card. RTL 8139. And this takes in the mapped memory, or memory, we'll call it, which is a slice U8. And here we go. And that's fine. So we'll say turn on RTL 8139, and we'll pass in the mapped memory. Cargo check, and we're going to say we're just gonna post this guy in here. Or maybe we can read the datasheet and understand why this is true. So config register 1, config register 1, config 1. Where does this, is this really not defined, explained anywhere? Here. Configuration. So maybe I'll look up config 1. And is this guy? Nope. Configuration register. Let's look at this. Maybe this will. Here we go. Ah, okay. So this guy says that we basically disabled memory mapping. This seems wrong. Oh, because everything else, these are read, right? Read, write. We cannot disable memory map or IO mapping. And we can say L-wake active mode. So we're setting this to active 0, sure. Which is default value. And driver load. Software may use this bit to make sure that the driver has been loaded. Writing 1 is 1, writing 0 is 0. When the command bits blah, blah, blah. I guess we'll just write here that this is safe as initializing all. What does it say to do here? Where, come on, let's see it. So to set the L wake and LW pattern. So really all we're trying to do is write bit 4. The default value is 0. So I don't really understand why I have to do this at all, to be honest. Send to set to active high. This should essentially power on the device. Next, we should do a software reset to clear the RX and TX buffers. So given that I see that the default value here is 0 already, and that's what they want, I think that we can skip this. And I will skip this until I find that I have something else to do, because I think this is bullshit. Okay, next we have to software reset. So clear the RX TX over defaults, bring everything to defaults, do this, the possibility of still being garbage left in the buffers, blah, blah, blah. Sending 010 to the command register will send RTL 8139 into software reset. Let's see if that's true. I don't trust these wikis. I trust the datasheets. But the datasheets also lie, so it's going to be fun. I don't trust anyone, is really what I'm saying. Okay, so const command register offset is a... Oh, I lost it. 0x37. And here he's saying that I send 37 there to set software reset. Oh, sorry, not 37. I send a 0x10. So let's look at that. Command register. Let's see your docs, baby. So that's bit 5, 4. 0, 1, 2, 3, 4. Reset. Yeah, okay. Sure, I'm okay with that. Function reset device. And we'll take in the mapped memory. And we'll say mapped memory command register offset equals we'll say let the value is 0, val set bit 4, and we'll pass it val here. And now we need to import this like utility class to set bits. Util bit manipulation set bits like this. Well, and we set this to true. I guess theoretically we should like read this and only write this specific bit, right? Mapped memory command register offset, and we'll say reset device register value is printed in hex, probably is nicer. And let's go into main and enable debug logging here. So I think that this is, I can do like a slice of tuples. So this is kernel RTL 8139, and we want to set this to log level debug, and then just call into on this. So I just need to import the right thing from the logger, which should be in logger log level. And let's cargo run and see what happens. So first of all, he doesn't like that into. I was certain that that worked. So hash map from, I thought that this worked. Arguments from this function are incorrect. Let's check. So he expected strings, not stirs. God damn you. God damn you. Okay. Didn't I import this? I must have undone too much. Log level. Okay, we are chilling. So we have debug logging enabled here now. And in here now we can say reset device mapped memory. And if I cargo run, we should now see the debug log that did in fact previously have the lowest bit set, which means buffer empty, but he's 0. So that's fine. I just wanted to make sure that I wasn't like clobbering these values. But that's fine. Okay, we'll leave that in for now. I like that. We've now performed a software reset, blah, blah, blah. And now we need to initialize the receive buffer. So, right. So when the chip retrieves data, it needs to put it somewhere in RAM. And so we need to tell it where that is. And so that means that we need to give it some memory. And now the question is, like, how much memory do we have to give it? Okay, so let's look at the receive buffers. Wow. Scrolling. Receive. Okay. So, because I need to set how much, I need to pre-allocate this space in the driver somewhere in order to like let it be written. And I need to know how much space I want to pre-allocate. So the configuration register, none of this is saying like, oh, buffer length. Okay. So 64K plus 16 bytes. So I guess I should, for each of these, I think, let's look at this again. So we will send the chip a memory location to use as its receive buffers. One way to do it would be to define a buffer variable and send that variable's memory location. Okay, so I think if I'm, sorry, I'm starting because I'm lost. If I remember correctly, there's multiple receive buffers. And that's all not true. There are only multiple transmit buffers. Okay, so I can just set this receive buffer to, what was it, 64K plus 11? But I guess it depends on what I configure. But I will just configure max size, because fuck it, you know? Buffer config. Where was that? I should have kept note of receive configuration register. So 0x44 to 0x47. This register is used, blah, blah, blah. And these are little Indian. Okay. Okay. So now we can say init receive buffer mapped memory. So here, init receive buffer. The first thing he's going to have to do is he's going to have to like allocate memory for writing. Then he's going to set configuration register to point to memory. And then we're going to set size of memory. Okay. Easy peasy. So we need to take this thing at offset 44. So we'll say that the receive config offset is 0x44. And this is a 4-byte register. And so we're trying to set bits 11 and 12. Set size of memory. So this is set bits 11 and 12 on receive config. Okay. Now we also need to set the, what was the command to set the buffer? Here we go. So 0x30. Oi. So much like scrolling. Register descriptions. 0x30 is the RB start. So RB start offset. Const RB start offset is a use size. Here's 0x30. Write address to RB start. And we have to allocate the memory. So allocating the memory is come on, baby. Command interrupt status. Where wasn't I a receive configuration? This is wait. 64K plus 16 bytes. So let receive buffer is a box new. And we'll just say this is a U8 slice 64 times 2024 plus 16. Okay. We need to import box because it's not free here. It's alloc boxed box. So box is like Rust's type for how do I say this? God, I'm blanking. Wow, that's crazy. Sorry. Rust's type for scoped heap allocation. So that's what we're trying to do here. And what I'm worried about here is that this is going to allocate 64 bytes on the stack before creating the box. So there's probably some way for me to ask for the allocation without initializing it. And that's actually what I want. So I can say box of type U8 64 plus 1020 times 1024 plus 16. All right, so that's this. And we can just call this new uninit. And he doesn't like that for some reason. Cargo check. Because that's an unstable library. Fuck. Allocates memory on the heap and then places X into it. So I want to avoid this. So I guess what I should do actually is I can make this out of a vector and then convert it into a box, which is a stupid way to do this. Is there really no way? From raw, no. Into raw. Very odd. Allocator leak. Let's do a quick Google. Rust allocate box array without stack. Is that a stupid? Here we go. That's what I want. And use a vec into boxed slice. Yeah. Oh, he's saying the benchmark. Yeah, sure. I don't really care about benchmarking. Then you can use. Yeah. Okay. So that is what they're saying. Is they want we do want a box like this. Okay. So I guess I actually want box slice of U8. And we'll say let Rx buffer is a vec with capacity. So this is from the alloc crate. We need a vector like this. And our vector is going to have capacity 64 times 124 plus 16. Configuration register 0b11 says this is the size. Okay. Easy. And we now need to look at how to convert this vector into a box slice because I don't want to like accidentally grow the array or move it around. So the box slice is actually very important to me. into boxed slice. The vector has excess capacity. Its items will be moved into a newly allocated buffer with the right capacity. So I actually want to extend this like with unallocated. So there's a way, if I remember correctly, to just change the capacity without actually allocating the memory, or without like initializing the memory, which I think is fine here. I just need to find that call. Because I don't actually care what the contents are, I'm going to assume that the network card is going to initialize the memory the way it cares about. And so there's no need for me to like pre-initialize it over here, you know? So I guess I can just look for unsafe, because I know that this is unsafe. Get unchecked as pointer. Swap as chunk, split, align. Set len. Forces the length. This is a low-level operation that maintains none of the normal variants of the type. Normally changing the length of the vector is done using one of the save operations, say truncate, resize, extend, or clear. Sure. New len must be less than or equal to old to capacity. Okay. And these elements must be initialized. But I know that like I don't really care about the U8s being initialized, so we'll say this is mutable, and we'll say rx buffer set len to rx buffer capacity. And does it say less than or less than or equal to? Less than or equal to. Solid. And now we just say this is the buffer into boxed slice. There we go. So this guy's going to return this box slice here because we need to keep the memory around for the driver to be able to write to it. Cool. Now we've got that out of the way. Set the configuration register to point to that point of memory. So here we have the RB start offset. So we'll say mapped memory RB start offset plus 4. And we actually want to write the memory address into this directly. So I guess we can just say std mem transmute. And we can just write the address here. So this is rx buffer as pointer. And let's see if this works. It looks like it does. And we'll return the rx buffer. And does it still allow that? No, he's mad at about a couple things. One, std doesn't exist, so it seems to be core mem. This doesn't have a known size at compile time. That makes sense. I thought that I could assign a slice like this. Okay, so let's see. Let temp equals this. Aha, so this needs to be and mute, like this, I guess. Cannot assign to this expression. I thought I could. Rust assign multiple values in slice. Rust assign array to slice. That's what I want. It doesn't like that. So copy from slice. Copy from slice. Okay. Sure, I can live with that. Cool. Probably I should just debug print the mapped memory before and after to make sure that it's something sane. So let's say that we wrote address. This is the receive buffer address that we passed in to memory. Memory is to device. Device has, and we'll just get this back. And I think I need to throw a question mark on there as well, but we'll see. So the first thing that we want to do is rx buffer as pointer, and then we want to write mapped memory rb start offset, rb start offset +4. Okay. Cargo check. It's going to be mad at me for some reason because I fucked up. Unclosed delimitator. Sure. Cargo check. He's mad because I can't print that, so probably I just have to like throw a question mark on here somewhere. I think like question mark X maybe. Cargo check. Other way around maybe. Cargo check. Size is not implemented for this, so I have to actually take this as a slice. Cargo check. He doesn't like this because I can just debug print the pointer. It's not like a value that I can hex print. And expected box U8, but instead he found a box something. Am I high? Oh, I probably just don't put the ampersand here. Cargo check. Nice. Cannot transmute between types of different sizes or dependently type. Okay. So we actually need to do this as pointer as usize. And usize is 32 bits and the target is 64 bits. Do I have to do this, like take the whole slice shit? Or maybe pass them as a reference? Doesn't have a size, no compile time. Okay, let's make a temporary here. So we'll say let pointer array is a U8 with 4 bytes, and he comes from this. Right? Then I just copy from the slice pointer array, and hopefully everyone is happy now. Cargo check. Cargo Clippy. So actually Clippy has a lint for this, it looks like. It's telling me he doesn't like 2 NE bytes. What is this? 2 NE bytes. Return the memory representation. Oh, nice. That's fancy. So I can actually say rx buffer as pointer to any. Where is it? Oh, it says U size. This is the U size that has it. So here I say 2 NE bytes. Very fancy. Very fancy. Okay, so Rust doesn't like this U8 for some reason. Is this actually like straight up illegal? This is like unsound probably for some reason. Setlen call, it calls vec with uninitialized elements. This is commonly caused by calling setlen right after calling a new default with capacity reserve. It creates a vec with it which leads to undefined behavior with most safe operations. Notably, uninitialized vec U8 must be used with generic read. Moreover, must not be used with generic read. Why? What the fuck? Why is this undefined? Why is this undefined? Does somebody explain this to me? There's something I like clearly don't understand. I understand that like maybe on init is like a type to like flag this, but why? Read on, oh, because the reader might read the value inside. Oh, that's so dumb. And obviously I'm not doing that. Oh, but no, because the value should, like, why would it shouldn't. I'm wrong again. Because this should just be like any U8s. Any U8 is valid. So just taking like garbage memory and spreading out my RAM to like setting those to be valid, like those are initialized. So why is vec U8 set len undefined behavior Rust? Can someone explain it to me? New lint, dangerous use of vector. I commonly to grow vector and fill the uninitialized data. This is dangerous because it exposes uninitialized read memory to be read and dropped on panic. Okay. See, here's my type, so initialize me maybe for more details. From a low level implementation, which generally means that some region of memory has been declared to be yours, but previously used for something else, you're not guarantee the bits. Sure. You were essentially reading random bits, so you're probably going to behave randomly. Sure. I don't care. It's almost always a serious bug to read from uninitialized memory. I disagree. Although you could certainly construct cases where that's not the case. Okay. Now, this model of a single process for single memory is required blah, blah, blah. For security reasons, memory first required from your operating system is to be at all zeros, blah, blah. Theoretical perspective is a bit more strict, blah, blah, blah. In an initialized state, the compiler may assume MAME has whatever value it wants. Okay, sure. So if Rust knows that it's uninitialized, it knows that I can't read, and so then it might do something fucking stupid. Fine. Oh, that's so stupid. I get it though. I should have seen this one coming. So can I just make this maybe uninit? Is that stupid? Do I just have to initialize it so that Rust knows? Or maybe I can just call maybe on init and then assume init. The rules are so complex. Yeah, the compiler in general assumes variable is properly initialized. This invariant is almost so even unsafe. As a consequence, zero initializing a variable reference of type causes instantaneous undefined behavior, no matter what that reference ever gets used to be accessed in memory. Oi, 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 oi. That's so stupid. This is exploited by the compiler for various optimizations, such as aligning runtime checks. Yeah, it makes sense. So this is also undefined behavior. Okay. So how do I have to set it? You can use maybe an image to implement out pointers, but hardware is initializing it. So why, like, how am I supposed to flag that to the compiler? Initialize an array element by element. Initialize struct field by field. So we can write to pointers. Guaranteed to have the same alignment. Ugh. You know what? That's so stupid, but I'll just not do it this way. It's so dumb, but that's fine. So I guess for the sake of Rust's compiler, we will just fucking slam it with zeros. Slow zero filling initialization. What do you want from me now? Is there a way to fix this? Yep. Sure. Use instead vec 0. Yeah, okay. Okay, vec 0 len. God, I'm so mad at you. I'm so mad. But it's fine. It's fine. It's fine. You can tell I think it's fine, because I've said it like 40 times. Okay, so this is unnecessary, unsafe now. And all right, we're chilling. Cargo run. Let's see what we get. So we wrote address 7FCFDE2 device, and device has 0000. So clearly we fucked up. So let's print line pointer array, which I can print as x question mark. Right, so the pointer array is reasonable. So 7FCDE2, so that's in the correct order. So why is writing that out not working? RB start offset. Like, I literally just wrote it here. Let's make sure that this is right. So we need to out port D. So send a 32-bit memory location to RB start. But we're not using this mechanism. We're using memory mapped IO. And for some reason that's not working. I wonder if we can write anything anywhere. Like, if we read this back, like, do we get anything from this? Reset device register value, switch from 0x11 to 0x1. Oh, it was, let's print before and after. So before we got 0x1, we got 0x1, and now we got 0x1. So something clearly happened. Sure, because we triggered a reset, so the bits changed. Okay, so we can in fact write to it. Writing to it is doing something. It is in fact doing something. So the question is why, when I try to give it my like pointer to like write to, why is that being rejected? Oh, once that byte is sent, the reset bit must be checked to make sure the chip is finished reset. I could have finished reading here. But no. No, I couldn't be bothered. Okay, so this is while mapped memory. Okay, so while mapped memory command register offset get bit 4 I think that's it. Get bits. We need to import this so that we have that function. And we do, in fact, wait, so this is while that bit is not equal to 0. So if I do this false, I wait forever. It never resets. So this is while not is not equal true. Or sorry, while this, yeah, sure, that's what they want. Unused parentheses, sure. So after I write the receive buffer, is it maybe not readable? That would make sense. Let's look at the receive buffer address. Maybe we just can't ever read it. It returning 0000 is pretty suspect. You know, this is read and write. So can I maybe while or loop Oh, fuck. Could this get like optimized to the point where this while loop doesn't run? Because assuming... Okay, so this whole mechanism of using map memory through a mutable slice is fucked. Because he's assuming that no one else can write to him. Oh, that's annoying. So we need to find a way to flag to the Rust compiler that like hardware might be talking to it. So Rust memory mapped hardware. Like, is there a way memory mapped registers? Like, there's got to be a way to make sure that he doesn't accidentally optimize that shit out. I guess if I just stick it in an unsafe cell, or maybe if I use the pointer directly. Yeah, okay, let's just try using the pointer directly. That's frustrating. But... Well... I guess we know it's not optimizing it out right now, though, because... the value's changing between what we sent and what we got back. But it does seem dangerous. I'm like sketched. Rust mute slice hardware mapped. I don't know how to like... Are volatile. Yeah. The best I know is to use volatile cell. Okay. Which is just essentially... probably the same as unsafe cell, maybe? Rust, let's see. Rust volatile slice. Write volatile. Performs volatile write memory the given value without reading or dropping the old value. Volatile operations are intended for to act on I/O memory and are guaranteed to not be elided or rewritten. Okay. So I guess I just actually have to use the pointer directly instead of the slice and then use volatile writes everywhere. Fine, fuck it. We'll do that. So this should be mute U8. And everywhere where I'm working with a slice of U8s, I should use a pointer. And we'll call this base. And we'll just slowly work through all of these. So base.add the offset dot read volatile. And now we do the same thing. We say base add command register. Let's say that the command register is this. We don't have to do this add all over the place. And here, then we can say the command register. We do a volatile read from it, and then from the command register, we do a volatile write of val, and then we can say that while we do command register volatile read get bit. Okay, cool. And now we do the same thing here. So we take in base as star U8. And here we say let RB start equals base add RB start offset. And we'll say RB start. Is there a copy from pointer array as pointer array dot length? And is there a copy from volatile? Like, great. Right, volatile. Let's see what kind of volatile. Right, they only have write and read, which means I actually probably have to write each byte of it manually. Write volatile should not drop the contents of dist. This is safe, blah, 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 blah. Sure. So I do probably just have to write it byte by byte. So you say for b in pointer array, and we need to enumerate this. So it's like ib pointer array dot in iter enumerate. Oi, oi, oi. And then we say rb start add I, and then we write volatile, and we write the b, and we need to dereference it, and we need to make this function unsafe so he stops bitching at me. God, shut up, Rust compiler. I get it. And now we have to read volatile. So what we do, we make this mutable, and we do the same thing. We do pointer, we iterate over length here, and we try to read the value back. So this is from 0 to the length, and we get this, and we say read volatile, and we say pointer array I equals this. Jesus. And we will just print this now. So we tried to wrote address this to device, and pointer device has pointer array. Cargo run. He's gonna get mad because there's a lot of stuff that's not right anymore. So mapped memory is mute u8. We need length. I guess the length doesn't need to be stored because we are asserting that it's the right length. And now we don't do this from raw parts shit. And mapped memory. Mapped memory. This is now mmap range start. And this is base, and we'll say base is mmap range start. Okay. Unimplemented here. And let's run. So we did all of that work to make sure that we're doing volatile writes, and they don't like it. It's still not getting what we want. So I wonder why. Why? I wonder if it's just like byte by byte write that we're doing. Maybe it doesn't like that. What if we change this as to a mute u32, and we can say rb start volatile write the rx buffer pointer as a u32. And we wrote the address this, and device has rb start dot read volatile. Cargo run. Oh, there we go. Fuck yes, fuck yes, fuck yes. Okay, so we have to do align 32 byte writes, I guess. Maybe. But okay, so we do have to write that in one go. It's crazy to me that that's different, but it is what it is. Okay, sick. So we've proven that we've uploaded the read buffer address to the device. And we can just kind of keep this guy in here as a debug thing for later. And now we just need to set the size of the memory to be what we allocated. So that's in the config register. Command register, interrupt status, transmit configuration, receive configuration, which is a 4-byte. Okay, so we'll say let receive reg is base.add receive config offset as mutable u32. In here we get the previous value, so that prev is receive reg volatile read, so because we know hardware might access this memory and we need to tell Rust like, hey, shut the fuck up and just read what it says. Then we set bits 11 and 12 to 0, 1, 1. So we'll say receive config val, and these should actually also be receive config register. And we say, make this mutable so we can edit it. We say receive config val set bits. The shift is bits 11. We set 2 bits for bits 11 and 12. We set this to 0B11. And then we write it back, baby. So here we'll say previous receive config register value, and we'll just write in receive config val like this. And new receive config register value is this. So we'll say so first we need to receive config reg write volatile, and we set the value that we just modified. We want this in hex actually, or maybe even binary. Can we do :b here? And yeah, fuck it, hex is fine. And we need to read it again for the debug info. What do you mean it's not used? It's used in this debug print right below. What the fuck are you talking about? Oh, I hate everything. Okay, cargo run. So, oh, I see. Okay, fine. You got me. You got me. I have to pass it in like this. We do the same thing here. It turns out that that warning I was mad about is actually, he was right. And I hate it when he's right and I'm the one who can't program, but it is what it is. Okay, so we have in fact set those 2 bits. We have confirmation from the logs that those are being set, and so now we can say that we've like initialized our receive buffer. Holy shit, that took a long time. But we're getting a little better here. Now, probably we should split this out a little more, because if I look back at this, I'm like, what the fuck is this doing? It's just like, it's hard to grok. So let's say unsafe function generate receive buffer, and this takes it just returns a box U8 like this, and that just takes this first shit. Easy. So we say let rx buffer equals generate receive buffer. This doesn't have to be unsafe. Then the next thing that we're gonna do is we're gonna say, here, we'll put this comment here. Configuration register says that this is the size. Cool. Now, after we get the buffer, we're going to write buffer write receive buffer address. It's going to take the base, and it's going to take the address, and this is also going to be a mutable U8. And this is just going to be this shit. And this is an unsafe function because it's working with memory directly. And we're going to take in adder. And maybe we call this a const U8. It doesn't really matter. Yeah, we'll call it mutable. Okay, and now we have to call this function as write receive buffer address, and he is base, and rx buffer as pointer, like this. And now all of this is like debugging information, but we're going to say unsafe function set receive buffer size. And he takes in base, and that's the rest of this. There we go. And so here we say set receive buffer size base. There we go. That's much more digestible. So why doesn't he like this? As pointer. Oh, this probably has to be like as mute pointer. And we have to make this mutable, or else he'll think that I can't write him. Cool. I am happy with that. Yeah, it's sick. So let's fix this log mac function after we switched from a mutable slice to a raw pointer. So let's say for I in 0 to 6, we say, well, we have like let mute mac equals 0, 6 bytes, 6 bytes of zeros. And then we say for IV in, what is it? Mac, iter, mute, enumerate is like the Rust way to do this. So we get like indexes and values. We say star v equals base self base volatile read, and we need to add I here. And of course we drop this into unsafe, and then we say print line, or sorry, info mac address is hex print this array debug mac. Okay, let's see this. Cargo run. Everyone happy? We do still get the MAC address 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C. Holy shit. Okay. Okay. So our read buffer is now initialized. This is taking a lot more time than I initially thought it would. But we're making progress. Okay. So now we have to set up these interrupt service registers. IMR bits line up the ISR bits to work in sync. If IMR bit is low, then the corresponding ISR bit will never fire an IRQ when it comes time to happen. IMR is 0x3C, ISR is located at 0x3E. So what the fuck is IMR? 0x3C. 0x3C. 3C. Interrupt mask register. Oh. Sure. So this tells me to like enable mat interrupts on that port. And the interrupt service, this is like just wrongly named according to the datasheet. Oh, maybe this is the wrong one. Interrupt service register is 0x3E. So they're saying 0x3E is interrupt service register, which this is saying is interrupt status register. I guess you could argue that these are the same. So interrupt service bits are always set to 1 if the condition is present. Okay, so probably hardware sets the interrupt status register to 1, and then that generates an interrupt. Right. Maybe. Well, we'll see. And So this is like the stateful one, and then it checks the mask to be like, can I fire an interrupt though? And then it goes like, yep, you sure can, Betty. And then he fires it. Sure. Okay. So sets the TOK and ROK bits high into the mask. Sure. What are the other ones? Transmit error, buffer overflow. Yeah, okay. I guess the minimal thing that we need to do to get working is just the receive okay and transmit okay. But in reality, we should allow everything. But sure. We'll follow the tutorial for now. I'm okay with it. That seems kind of reasonable. So I guess before we do that, though, we have to set up our interrupt service handler. So how do I get the interrupt? ISR handler. Here we go. You have to write the bit. Of course. So how do I like know where does this interrupt go? Presumably PCI interrupts. Are like a thing that can happen. Message signal interrupts. Mantor and PCI devices. PCI. Well, let's look up like interrupts here, maybe, and see if there's like a PCI number that goes through the PIC. How do I know? How do I know? Nothing in here is screaming at me. The datasheet says reading the register is enough to reset it. This is not the case in QEMU, so I have to write this register in QEMU. Sure. But where does the interrupt go, man? Boy. I guess like we can just turn on the interrupts, and as long as they're unmasked, they'll start crashing me. But that's not true because my interrupt like PIC, whatever it's called, something interrupt controller, that's not set up to like receive. So I need to figure out how these are connected. RTL 8139 interrupt PIC, right? That's, here we go. How do I make sure that the RTL is connected to the PIC and EQ? PCI configuration space. Okay, let's go back to the PCI thing then. PCI configuration space. Somewhere in here, they're claiming that I should have the interrupt number. So let's just interrupt. Command register, interrupt disable. Okay, we're close. Interrupt status represents the state of device int x. I'll have SITO1, the command register, interrupt disable, blah, blah, blah. That's not what I'm looking for. Interrupt pin. Okay, so this is a generic device. Interrupt pin specifies which interrupt pin the device uses, where a value of 0x1 is int A, 0x2, int C. Means the device you do not use an interrupt pin. What does that mean? Where is that form post? So I read it from the PCI configuration space is RQ line 11. Okay, so wait, whoa, 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 hold on. So this is only on a PCI to PCI. Oh, yeah, okay. So interrupt pin specifies which interrupt pin the device uses. What the fuck is int A, int B, int C number? What the fuck? Okay, I guess we'll read the value first, and we'll kind of work backwards from there. So here we can say pub function get IRQ number, right? And he takes in this guy, and we start by reading a register, which is register F, according to this table. And interrupt pin is bits 8 to 15. So we say reg get bits 8, length 8. So we're shifting by 8 bits, getting 8 bits, get bits 8 to 15. So RQ equals this, and print line We'll just print this, yeah. IRQ is this, IRQ. Okay. And then in main, or not in main, in our network driver, we have to call this somewhere. So we'll just say here, RTL device get IRQ num. And let's kind of just see what he says to me. Cargo run. Let's get it, baby. IRQ is 1. Does that line up with anything? So here he says a value of 1 is int A number, int B number. So what is that? Int A, x86. External interrupts. Okay, so is there... What the fuck is that? What does it mean? Is there like an assembly instruction? It must go through the service handler. PCI device int A, PIR, PRQ. This is a lot of things I haven't seen before. Does this mean that like the pick is not sufficient? Oh, I hope not. So I think I saw somewhere that there's like 2 ways to handle external interrupts. Somewhere. And that I'm using like the dumb way, the dummy, stupid, dumb boy way, these PICs. But I think that there's these things called like APICs. No, I thought I saw a second way. Okay. So interrupt 1 on this guy is reserved for keyboard interrupt. So I'm like fairly skeptical of that thing. That like that 1 that we received when we read the configuration space. I'm skeptical that that's the right interrupt. So can I do let's see, os dev pick PCI interrupt. Let's just kind of get through this. Show results with PCI. IO APIC and PCI interrupts. Okay. Shit. IRQ lines for PCI devices. And IO APIC. I found pick space interrupts already. Blah 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 blah. IO APIC. What is IO APIC? OS dev. What does that mean? Intel Advanced Programmable Interrupt Controller used to distribute external interrupts in a more advanced manner than this guy. Interrupts can be distributed to physical or logical clusters of processors, each by prioritized. Each IO contains 24 external interrupts. Okay. So does that mean that this guy can't, the old version doesn't handle PCI? Yeah. Okay, console 8259 pick QEMU PCI. I'm trying to build a network card driver. Hey, this guy's like me. And he is struggling. In general, the legacy ISA int number are mapped onto the IO APC interrupt line. So you'll find that the interrupt line of your PCI device is one of int 0 to 15. The interrupt lines covered by the legacy, you can also use those instead of the IO APC. However, this is not guaranteed to be present, and ACPI requires it to be disabled by the OS when enabling ACPI. Okay, so in the real world, I'm supposed to use the new version. But since I'm already working with this, people are saying that it seems like it's okay. You can rely on MP tables to accurately tell you how the interrupts, blah, blah, blah. PCI devices may support. Okay, so I guess what we can do is, for now, we can assume that this interrupt number that we're getting is, in fact, consistent with the pick. And since it's in the first 16, it's wrong. I would be nice to get some confirmation here. So if we reroute the interrupt lines, can we get like different values read? That would be like a good test. So QEMU set interrupt line for network card or something like womp 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 womp. Oh my god, you're so slow. I just blah 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 blah. Okay. Somewhere he's asking the question I want. No. Hardware interrupt simulation. Yo. QEMU set interrupt line? Maybe? This is way more complex than I was looking for. Fuck. I was so hopeful. I guess another, like an easy way to trigger, to like test this, easy, is if my network card, if I like set the masks so that my network card triggers interrupts, then try to transmit some packets and we don't see an interrupt trigger, then we'll know that something's wrong. So let's just like proceed with the assumption that that is correct. Like that seems fine to me. Okay, so let's request the interrupt number from the PCI configuration space, and this will return me just a number that we're assuming is in pick space for now. So this will just be fuck it. We'll just like return an U8 for now, and we'll force these guys to map it later. Then we just return IRQ. Boom, bing, bang, boom. As U8. And then here we can say the IRQ number is this guy, and we can like set up our interrupt handlers. So we need to give like pass in a reference to our like interrupt handlers, and this is like interrupt handler data, I think is what it was called. And in main, we need to pass this guy in now when we're initializing our driver. So here we pass in interrupt handlers, probably as this doesn't have to be mutable, sorry. This is a internally mutable thing that we've written before. Local variable with the same name is interrupt handlers. Is that not right? Okay. And now I should be able to say, let's assert IRQ num is less than 8 for now because we can only handle the first 7 generically. And we will say interrupt handlers register. We'll register something for IRQ ID. Pick 1 and IRQ num. And I guess then we also have to pass in our handler. So, and here we'll just print line AO. And now hopefully if we do it all the rest right, we should start seeing like print line spam later. And we'll just assume that this is set right, and let's run cargo check. Cool, and cargo run. Uh-oh. Oh no. Did my PC crash? Are we good? Oh, we're good, but my camera is delayed now. So can I just like quickly re-initialize that guy? Remove. Are you sure you want to remove the video capture device? Yes, and let's add him back now. Video capture device. And are we back? Where is he? I lost him. We need my camera, or else how will you guys know that it's me? Video capture device. This comes from the camera. Input camera 1. Do I have to change the video format? Ugh, that's annoying. That's annoying. Okay, well, we'll just do the rest of the stream with no video, with no camera. But at least everything else is responsive. Okay. So let's go back to interrupt handling. So let's see. Where were we? We were going to try to transmit some packets, and if we set these like interrupt registers, we like mask these guys, we can assume that we will get interrupts, and we'll see them printing. So for now, let's just say init imr, and we'll say mmap range start add 0x3c write volatile this number to enable the like masks that they want. So this is like this, and I think that this is a 32-bit register, so we might need to cast this. Let's see, this is 0x3c, and I lost my data sheet, so let's pop it open, and we'll just say 3c. Where are you, baby? Interrupt mask register. This is a 16-bit register. So we just need to as mute u16 to ensure that we get the right like bit width as we write whatever. Okay. So now if we were to write something, we should see our interrupts trigger. So enable receive and transmit, configuring receive buffer. We did kind of like half configure this earlier, but we did not set these values. But also we don't really care for this test that we're doing. So we'll come back to receiving later, and we'll just start transmitting something now. Yeah, let's take a look at that. So let's actually, we've gone a while without making any progress, but we have like done stuff. So let's just kind of initialize receive buffer. This is done. We software reset, that's done. And figured out volatile writes. And now we're working on transmit data / prove interrupts. Okay. So let's get back over here and let's just like try to fucking get a write going, and we'll see how that goes. So it uses a round robin style for transmitting packets. It has 4 transmit buffers, yep, and status registers. Each transmit start register is 32 bits long, and their IO offsets, these guys, sure. Yep, that's consistent with what I've read in the docs. Transmit status command registers are also each 32 bits long, are in IO offsets, blah, 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 blah. Yep, each pair of transmit start and status registers work together. Yep, cool. So there's, yeah, sure. So I only have to work with one first. After performing a controller reset, the controller ignores all transmit registers except for pair 0. Okay, cool. After software transmits a packet using these registers, a round robin counter increments. Yep, so then we use 1, blah, 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 blah. Which is the last transmit. Counter with overflows goes back to 0. So how do I do anything here? Contains various bit fields that control the transmission of the packet. For the full format, look at the specification. Yeah, okay, fine. I'll read the data sheet. Fine. Jeez. But we'll start by just saying the data size. So probably this starts at 0. When this bit is set to 1, the controller is idle and not performing any dynamic transfers on this descriptor. The driver sets this bit to 0 to tell the controller to start transmitting the packet. The bit remains 0 until the packet is copied. Okay, so that's actually really easy. So I can just give it some data, and then if I see it set to 0, I should see an interrupt happen before that. So let's first write out transmit address 0. So we'll just make like a vector. We'll just like shove some like dummy data in here. So we'll say like vec and we'll say 1, 2, 3, 4, 5, 6 or something, right? And then we'll set the data size in the configuration register. So that's transmit status descriptor 0 at 0x10. Is that consistent with what they said here? 0x10. Yep. So let transmit config equals the mmap range start add 0x10. And this is, I think, as U16. Then we have the transmit data equals mmap range start add 0x20 as mute u32, or mute usize, maybe we should say. Transmit data, we volatile write the we'll just call this data. We have to write data dot as mute pointer. Right, he's gonna do some accesses there. And we need to convert this to usize. Here, we read the values in the config, right? And then we set the own bit to 0. So first we should let's read the config bit. So let's print line config big, just to like get a good feel, and maybe we'll just leave it as a print line for now instead of a log. Let's take a quick little peeky, and we see 8192, which probably means that transmit okay is full. Let's print this in hex just for confirmation, because I often get this wrong. 0x2000. So this is a bit 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 is set, which is the only bit that's not documented here. Let's go look at the transmit status register. So 1, this is a 32-bit register. What the fuck? Maybe I'm not writing the right thing. 0x10 transmit status register. Set to 1 if the packet was aborted. Courier lost. So none of these are what I expected to see here, where this says 0x10 has like data bit. So am I looking at the right data sheet? These are like different, but they are the same part number. So let's look again a little closer. Transmit byte count. Just be cleared by when the transmit byte count bits 12 to 0. Oh, it's down here. Aha! Aha! Yeah. So 14 is underrun. This was exhausted during transmission of a packet, but this should be set. Okay, but that's okay. So how do I? The driver sets this bit to 0 when transmit byte count bits 0 to 12 is written. Default value is 1. Okay. Okay, so let's try that. We'll say config.write our set bits. So the lowest 12 bits are the size. So switch to 0, length is 12, and the data is data len. And then we say config set bits, and we set bit 13 to 0, I think. The sets of data is set to 0 when the transmit byte count is set. Yep. And we'll say set bit 13 to false, like this. And let's print it again after. So now we have config 0x6. And Now let's write that. So transmit config write volatile. And here we're writing the config back. And here, nothing's really happening. We do, in fact, get... I got an interrupt here when I pressed a letter into the keyboard window, which indicates that the interrupt controller is, in fact... where is this guy? Sorry. So here... sorry. RQ, maybe? Oh, where was that table? Here. So here, ISA RQ1 is what happens when I type into the window. And it means that this value that we're getting back from the PCI configuration space for the interrupt handler is not running, or I'm fucking up my transmission. One of the two, right? And so what we can actually do is we can read back this own bit and see what happens. So we can just like pull this config for a while. So we can say loop. We can say transmit config read volatile. Let config equals this. And we can just say read bit get bit 13. So we'll say own is this, right? Because that's what it says in the data sheet, is like this is the bit that we say to say like we're using it in the controller or we're using it in our driver. And we'll just set we'll print line own for a bit. And just kind of see what we get. So these are true for a long time. And we'll say if own return. So what I'm hoping to see is break, I guess. Nice. Okay. So what we're seeing is we did see the transmit thing get set. Oh no, we didn't. We only ever saw it be 0, be true. Can we write like more data here? We'll say this is 0, and we'll write like 2 power of 12 minus 1. We'll write the maximum length we could possibly fucking write. Okay. And we do not ever see this get set. So let's can we print like the whole stat or the config bit? Config. So we get 2000 back. But we know that we wrote something else. Right? We know that we wrote config. And we got something else back. So what would be cool is if we could prove to ourselves that if we write the bits at the bottom, but we don't set the own bit, do we get that back? So let's try this. So let's print line what we get back from the config register after we write it. I'm struggling here. So we'll say after write 1 is what we want to see here. So after write 1, we see 8192. That's really good. Because, well, first let's see initial state. Initial state. Oh, shit. So after write 1, just nothing changes. That's not good. That's not good at all. So transmit config, we read it, we set some bits, we write it, and then we immediately read it back, and we don't get what we want. We don't see what we just put in, which is a little bit concerning. That is concerning. So log 2 8192. Just which bit is this? Oh, that's not lon. Is it lon 8? No. Log 8192 over log 2 is 13. And log 1 over log 2 is 0. So this is 0 index bit 13. Right? So if I log 2 over log 2, I get 1. Yeah, that makes sense. So log 8192 is the 13th bit, and in the datasheet, the 0 index 13th bit is the own bit. So this is supposed to be read-writable. If the total size and bytes of data, if the packet length is more than 1792, the TXQ will be invalid. Okay. So that's my bad. This should be only like 1790 or something. So we write to it, and we immediately get back that it's finished. God, that's annoying. I want to see the own bit set to 0 ever. But I wonder if it's just happening too fast. It's just too quick. We can look for like transmission okay or some form of like error bit. So this is, let's reread this as a U32. And here, this now needs to be U32. And, oh, okay. So we are seeing a change in behavior after this. After we write, that's really good. So let's come back here and see, womp, womp, womp. Give me a second. I'm stuck. I'm stuck. I'm stuck. Okay. So we want to set bit, and we never actually write. So here we tell it to go. And we say, oh, that's good. Okay. Cargo run. We're seeing some log spam now. Does it ever finish? Does it ever finish? No. But that's good. So let's reduce the data length here to like 25. We're not seeing that finish either. So here, why is all of a sudden this behaving differently? Probably because I'm using the U32 right now. So let's only print it after it changed. So we'll say let mute last config equals config. And we'll say if config is not equal to last config, we'll print it. And then we'll say last config equals config. As a way to like see only when something interesting happens. So after write 1, it's 25. And it just stays 25 forever. So that's interesting. I would think that we should see something happen. So what am I fucking missing, man? RTL 8139, I think it's called. What am I missing? So we have to configure the receive buffer, but that doesn't matter. Oh, enable receive and transmitter. That's a big one that I just didn't do. Okay, so after we init receive buffer, we need to set these high. So we say base, or the pointer to the beginning of our range is mmap range start, and we add 0x37, and we write volatile 0x0c, and this should enable transmit receive. And let's do this after we initialize the interrupts, and let's see if this does anything. Hey, okay, so that's a really good sign. So we see that what we've done here is we've initialized our like network card, and we've proven that we see a state change from when we write the register to when we receive it. And let's see if like what we see makes sense. So the thing we get back at the end is A019. So first let's what did we write before? Sorry. Sorry, one sec. We'll say let config is equal to what we read back. And what we wrote is wrote config. And so the initial state is we write 25 here, and we get back something very different. So let's kind of try to break down what we received back and see if it makes sense. So the first thing is 4. That's really easy to get from here. This is 0, 4, 8, 12. Sorry, what am I saying? This is 4, 8. No, yeah, 0, 4, 8, 12, 16. And 4 is 17, 18 or something. Bit 18 or 19 or something. Early TX thresholds. Okay, so it's bit 15 set. That's what we want to know, was the transmission okay? So let's print line T okay should be config get bit 15. Why don't I see this? Oh, okay, so transmission okay is true. And before was transmission okay false. Right, okay. So we see that we get the like own bit set false or set to true after it finishes. We see that the transmission okay flag is true. And so we have like a fairly good indication that writing to the Ethernet driver is like working as or to the Ethernet card is like working as expected. But what we do not have is like interrupts being fired when that transmission finishes. And I think that that's probably where I'm going to have to call it for a bit, because enable to get interrupts enabled, I need to read about this like interrupt handling negotiation between the PCI system and my CPU. I suspect that the like stupid pick mode is like maybe not good enough, and this like a pick is what I'm supposed to be using, and so I might have to loop back and try to implement this. I'm gonna do some reading off stream, but I'm pretty stoked on that so far. So we kind of have done enough to get some indication that transmission of Ethernet data will work, and I'm happy there. We also got like gained a lot of knowledge about like volatile read writes and Rust. What I like my intuition there on what was going to work was like totally wrong, and so it's good to know now that that's fixed. Yeah, thanks for watching. This has been a blast. If you're enjoyed and you want to see more, you can always catch up on YouTube, which is linked to my Twitch page. And if you're on YouTube, you can catch me live on Twitch at around like 2 Pacific time till however long I decide to stream for that day. So thanks for watching. Catch you on the next one. Bye.